There are places in the universe where the rules you trust simply stop working. Places where distance loses meaning, where time slows to a crawl, and where even light, the fastest thing we know, is trapped forever. These places are not science fiction. They are not theoretical curiosities anymore. They are real, measurable, and sitting at the heart of galaxies, including our own. They are called black holes. The idea alone feels impossible. How can something be so powerful that nothing escapes it? How can an object exist if it cannot be seen? And how did humans, standing on a small planet, orbiting an ordinary star, ever discover something like this? Black holes force us to confront an uncomfortable truth. The universe is not built for human intuition. The deeper we look, the more reality refuses to behave the way we expect. Black holes are the ultimate example of this. They are not just strange objects in space. They are places where our understanding of reality is pushed to its absolute limit. To understand why black holes are so important, we must first let go of the image most people have in their minds. A black hole is not a hole. It is not a tunnel. It is not a cosmic vacuum cleaner drifting through space and swallowing everything nearby. That image is wrong. In fact, it hides something far more interesting. A black hole is an object, a real physical object. It has mass, it can spin, it can collide with other black holes, and most importantly, it follows the laws of physics, at least as far as we understand them. But those laws behave very differently near a black hole. Gravity, which feels weak and familiar in everyday life, becomes dominant on a cosmic scale. On Earth, gravity pulls you toward the ground. In space, gravity controls the motion of planets, stars, and galaxies. But near a black hole, gravity becomes absolute. It overwhelms every other force known to science. To see why this matters, imagine standing far away from a black hole. From that distance, it behaves like any other massive object. If our sun was suddenly replaced by a black hole of the same mass, Earth would continue orbiting almost exactly the same way. Nothing dramatic would happen. This surprises many people, but it is true. Gravity depends on mass, not appearance. The danger of a black hole appears only when you get too close. As you approach, gravity grows stronger and stronger. Space itself begins to curve sharply inward. Paths that once led straight now bend toward the black hole. Even light, which normally travels in straight lines, curves and spirals inward. At a certain distance, escape becomes impossible. This boundary is called the event horizon. The event horizon is not a surface you can touch. It is not made of matter. It is a point of no return in space and time. Once something crosses it, the future no longer leads outward. Every possible path forward leads deeper inside. This idea alone challenges everything we believe about motion and escape. Everyday life, no matter how deep a pit is, you can always imagine climbing out if you have enough energy. A black hole breaks that logic. Beyond the event horizon, escape is not difficult, it is forbidden. But black holes were not discovered by watching stars fall into darkness. In fact, when the idea first appeared, many scientists refused to believe it. The concept of a black hole came not from telescopes, but from equations. In 1915, Albert Einstein introduced the theory of general relativity. This theory completely changed our understanding of gravity. Instead of treating gravity as a force pulling objects together, Einstein described it as a consequence of curved space-time. Mass bends space and time, and objects move along those curves. General relativity made astonishing predictions. It explained the motion of planets more accurately than Newton's laws. It predicted the bending of light around massive objects. It even predicted gravitational waves, ripples in space-time itself. But hidden inside Einstein's equations was something disturbing. Under extreme conditions, the equations allowed space-time to curve infinitely. They allowed gravity to become so strong that no signal could ever escape. These solutions suggested the existence of objects far more extreme than anything previously imagined. Even Einstein himself was uncomfortable with this idea. He suspected that nature would somehow prevent such objects from forming. Many physicists agreed. For decades, black holes were considered mathematical oddities rather than real things. That skepticism slowly faded as scientists began to understand how stars live and die. Stars exist because of a delicate balance. Gravity pulls inward, trying to collapse the star. At the same time, nuclear fusion in the star's core produces energy that pushes outward. As long as these two forces balance, the star remains stable. But stars do not burn forever. When a massive star runs out of fuel, the outward pressure drops. Gravity takes over. The star collapses inward at incredible speed. The collapse triggers a violent explosion called a supernova, briefly outshining entire galaxies. What happens next depends on the star's mass. If the core is small enough, it becomes a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. But if the core is too massive, even neutron pressure fails. Gravity continues its collapse without limit. That collapse creates a black hole. At that moment, an event horizon forms. Space closes around the collapsing core. From the outside, the black hole is born. This process is not rare. Throughout the universe, massive stars are constantly reaching the end of their lives. Black holes are being formed again and again, silently shaping the structure of galaxies. Yet despite their violent birth, black holes are surprisingly quiet afterward. They do not actively hunt matter. They do not roam space, consuming stars. Most black holes spend their lives doing very little, interacting only with material that comes too close by chance. This realization completely changed how scientists viewed black holes. They were no longer exotic anomalies. They were a natural outcome of stellar evolution. But the real shock came when astronomers discovered something even more extraordinary. At the center of almost every galaxy lies a supermassive black hole. These black holes are not formed from single stars. They contain millions or even billions of times the mass of the Sun. The one at the center of our Milky Way, known as Sagittarius A High, has a mass of about 4 million suns. How such enormous black holes formed is still one of the biggest questions in astrophysics. What we do know is that galaxies and black holes grow together. The presence of a supermassive black hole influences how stars form, how gas moves, and how galaxies evolve over billions of years. In a very real sense, black holes help shape the universe we see today. Despite this importance, black holes remain invisible. They emit no light of their own. Once matter crosses the event horizon, it vanishes completely from view. So how do we know black holes exist at all? The answer lies in their effects. Matter falling toward a black hole does not disappear quietly. It forms a swirling disk called an accretion disk, heating up to extreme temperatures and emitting intense radiation. This radiation can be detected across vast distances. Stars orbiting an unseen massive object reveal its presence through their motion. By measuring how fast they move and how tightly they orbit, scientists can calculate the mass of the invisible object controlling them. In 2015, another prediction of general relativity was confirmed. Scientists detected gravitational waves produced by two black holes colliding and merging billions of light years away. These ripples in space-time reached Earth and were measured with extraordinary precision. This was direct evidence that black holes are not just real, but dynamic and violent on cosmic scales. In 2019, humanity saw something once thought impossible. Scientists released the first ever image of a black hole. It was not a picture of the black hole itself, but of the glowing material surrounding its event horizon, warped by extreme gravity. It was a historic moment. A theory had become an observation. Yet even with these achievements, black holes continue to hide their deepest secrets. The boundary of the event horizon marks the limit of observation. Beyond it, our understanding collapses. According to general relativity, everything inside is drawn toward a singularity, a point of infinite density where space and time lose meaning. The The singularity represents a breakdown of physics. Our equations stop working. We cannot describe what happens there. This is not because the singularity is mysterious by nature, but because our theories are incomplete. Black holes expose the conflict between general relativity and quantum mechanics, the two pillars of modern physics. They demand a deeper theory, one that can explain gravity at the smallest scales. This is why black holes are not just objects of fear or fascination. They are tools for discovery. They are laboratories where the universe tests its own rules. As we move forward in this series, we will explore black holes layer by layer. We will examine how gravity becomes unstoppable, how time bends near the event horizon, and how scientists continue to study something that cannot be seen. Black holes are not the end of understanding. They are the beginning of deeper questions. They remind us that the universe is far stranger than our instincts suggest, and that curiosity, guided by science, can reveal truths hidden in the darkest corners of reality. Gravity is the quiet architect of the universe. You rarely notice it in daily life, yet it governs everything from the fall of an apple to the motion of galaxies across billions of light years. Unlike forces that fade or fluctuate, gravity never switches off. It acts on everything that has mass, and it acts endlessly. On Earth, gravity feels gentle because our planet is small on cosmic scales, but in space, where mass can accumulate on unimaginable levels, gravity becomes the dominant power shaping reality itself. Black holes exist because gravity, under the right conditions, is unstoppable. To understand black holes, we must first understand gravity not as a simple pull, but as a rule that shapes the structure of space and time. Gravity does not behave like a rope tugging objects together. According to Einstein's theory of general relativity, gravity is the result of mass-bending space-time. Objects move along the curved paths created by that bending. When space-time is only slightly curved, motion appears familiar. When space-time is extremely curved, reality behaves in ways that seem impossible. Stars are born within clouds of gas and dust that collapse under gravity. As material falls inward, it heats up, eventually igniting nuclear fusion. Fusion releases energy, producing an outward pressure that pushes against gravity. A star exists because these two forces are locked in balance. Gravity tries to compress the star, while fusion tries to make it expand. As long as this balance holds, the star remains stable. The lifetime of a star depends largely on its mass. Smaller stars burn fuel slowly and can live for tens or even hundreds of billions of years. Larger stars burn fuel rapidly. They shine brighter, grow hotter, and exhaust their energy much faster. These massive stars live dramatic but short lives, and their deaths are among the most violent events in the universe. When a star begins to run out of fuel, fusion slows down, outward pressure weakens. Gravity immediately takes advantage of this imbalance. The star begins to collapse inward under its own weight. As it collapses, temperature and pressure rise, often triggering new fusion reactions. In many stars, this process repeats several times, with different elements fusing in layers like an onion. But this cannot continue forever. There is a fundamental limit to fusion. When iron forms in the core of a massive star, fusion stops producing energy. Iron does not release energy when it fuses. Instead, it absorbs energy. At this moment, the star loses its final source of resistance against gravity. The balance that held the star together for millions of years collapses in less than a second. Gravity takes complete control. The core of the star collapses catastrophically. Electrons and protons are crushed together. Atomic structures are destroyed. Matter is compressed to densities beyond imagination. The outer layers of the star crash inward, rebound violently, and explode outward in a supernova. This explosion releases more energy in a few seconds than the sun will produce in its entire lifetime. After the explosion fades, what remains depends entirely on mass. If the remaining core is relatively small, gravity is stopped by quantum mechanical forces, the core becomes a white dwarf or a neutron star. These objects are incredibly dense. A neutron star packs more mass than the Sun into a sphere barely 20 kilometers across. Yet even neutron stars have a limit. Neutron stars are held up by neutron degeneracy pressure, a quantum effect that resists compression. But this resistance is not infinite. If the collapsing core is too massive, gravity overwhelms even this last line of defense. At this point, there is nothing left to stop the collapse. Matter continues to fall inward without limit. Density increases endlessly. Space-time curves more and more sharply. Eventually, a boundary forms where escape becomes impossible. This boundary is known as the event horizon. The formation of an event horizon marks the true birth of a black hole. The event horizon is not a physical surface. It has no thickness, no material structure, and no visible edge. It is a boundary defined by geometry. Once something crosses it, all possible future paths lead deeper inside. There is no direction that points outward. This is why even light cannot escape. Light always follows the straightest possible paths through space-time. Near a black hole, space-time is curved so severely that every straight path bends inward. Light does not slow down. It simply has nowhere to go. From a distance, a black hole behaves like any other object with the same mass. Its gravity follows familiar rules. Planets and stars can orbit it safely if they're far enough away. There is nothing inherently dangerous about a black hole unless you approach too closely. But as distance decreases, gravity's dominance becomes absolute. As an object falls toward a black hole, the difference in gravitational pull across its length becomes extreme. The side closer to the black hole experiences stronger gravity than the far side. This difference stretches the object lengthwise while compressing it sideways. This process, known as spaghettification, is a direct result of gravity's uneven pull. At the same time, time itself begins to behave strangely. According to general relativity, time slows down in strong gravitational fields. This effect has been measured near Earth and must be accounted for in satellite systems like GPS. Near a black hole, this effect becomes dramatic. To a distant observer, a falling object appears to slow down as it approaches the event horizon. Its clock ticks more slowly. Its light stretches to longer wavelengths. Eventually, it fades from view. From the perspective of the falling object, nothing unusual happens at the event horizon. It crosses smoothly, unaware that it has passed a point of no return. This difference in perspective reveals a profound truth. Time is not absolute, it depends on gravity. Inside the event horizon, gravity's victory becomes complete. Within this region, space and time exchange roles. Moving forward in time means moving toward the center. Avoiding the singularity becomes as impossible as stopping time itself. According to general relativity, everything inside is drawn inevitably toward a point of infinite density known as the singularity. The singularity represents the ultimate consequence of gravity's dominance. Density becomes infinite. Curvature becomes infinite. Our equations break down completely. Physics, as we understand it, can no longer describe what happens. This breakdown does not mean the singularity is meaningless. It means our theories are incomplete. Stephen Hawking was one of the scientists who explored this implication deeply. He demonstrated that singularities are not mathematical accidents. Under very general conditions, gravitational collapse must produce them. If general relativity is correct, singularities are unavoidable. This realization was unsettling. It suggested that the universe contains regions where our most successful theory fails. But Hawking did not stop there. He asked what black holes truly are, not just as endpoints of collapse, but as physical systems governed by deeper laws. One of the most important insights was that black holes are remarkably simple from the outside. No matter how complex the material that forms them, black holes can be described by just a few properties mass, spin, and electric charge. Everything else is hidden behind the event horizon. This simplicity hinted that black holes might not destroy information, as once thought. Instead, information might be encoded in subtle ways on the event horizon itself. This question, known as the black hole information paradox, would later reshape theoretical physics. But even without these deeper mysteries, gravity's victory alone explains why black holes exist and why they are stable. They are not temporary phenomena. Once formed, black holes can persist for billions or even trillions of years. Gravity does not merely create black holes, it uses them. Supermassive black holes sit at the centers of galaxies, including our own Milky Way. Their gravity influences the motion of billions of stars. They regulate how gas flows through galaxies. They shape the growth and evolution of cosmic structures on the largest scales. Without gravity's ultimate victory, galaxies might never form the way they do. The universe would look profoundly different. Black holes are not failures of nature. They are consequences of its rules. They show us what happens when gravity is allowed to reach its logical extreme. In the next part, we will step closer to the edge of the unknown. We will examine the event horizon in detail and explore what happens as matter, light, and time approach the boundary where escape ends. We will separate what science knows from what it suspects and from what it cannot yet answer. Because when gravity wins completely, the universe reveals just how strange reality can be. There is a boundary in the universe beyond which our understanding fades. It is not marked by light, walls, or matter. There are no warning signs, no sudden explosions, no dramatic flashes. Yet once crossed, it separates everything we can observe from everything we cannot. This boundary is called the event horizon, and it is the defining feature of a black hole. To grasp why the event horizon is so important, we must first understand what it truly represents. It is often described as the surface of a black hole, but this description is misleading. The event horizon is not a physical surface. It has no thickness. You cannot stand on it. It does not exist as an object. Instead, it is a mathematical boundary in space-time itself. It marks the distance from the center of a black hole at which escape becomes impossible. This impossibility is not caused by a sudden increase in gravitational force. Gravity does not suddenly spike at the event horizon. In fact, for very large black holes, the gravitational pull at the horizon can be surprisingly gentle. An astronaut crossing the event horizon of a supermassive black hole might not feel anything unusual at that exact moment. There is no shock, no sudden tearing of the body, no dramatic signal announcing the crossing. And yet, crossing the event horizon is a final act. Once it happens, no information can ever return to the outside universe. No signal, no particle, no light, and no message can escape. The event horizon marks the absolute limit of observation. To understand why this happens, we must return to the idea that gravity bends space-time. Near a black hole, space-time is curved so extremely that all possible paths forward lead inward. Light always travels along the straightest paths available to it. But near a black hole, even the straightest paths curve toward the center. There is no outward route left. This is why black holes are black. Not because they absorb light like dark paint, but because light cannot climb out of the warped space-time surrounding them. From far away, an object falling toward a black hole appears to slow down as it approaches the event horizon. This effect is not an illusion. It is the result of gravitational time dilation. As gravity becomes stronger, time passes more slowly relative to distant observers. The falling object's clock ticks slower and slower. Its light stretches to longer wavelengths, shifting from visible light to infrared, then to radio waves until it fades entirely. To an external observer, the object never quite crosses the event horizon. It appears frozen just above it, fading into darkness. From the object's own perspective, however, the story is very different. For the falling observer, time flows normally. The event horizon is not a special place locally. There is no physical marker, no dramatic change. The observer crosses it without noticing anything unusual. This difference in perspective reveals one of the deepest truths uncovered by modern physics. Time is not absolute. It depends on motion and gravity. Once inside the event horizon, the rules change completely. In everyday life, you can choose where to go in space, but you cannot choose where to go in time. You cannot move backward or sideways in time. Inside a black hole, this distinction collapses. The direction toward the center becomes as inevitable as the flow of time. Just as you cannot avoid tomorrow, you cannot avoid the singularity. This is not a metaphor. In the mathematics of general relativity, the singularity lies in the future of everything inside the event horizon. Avoiding it would require moving backward in time, which is impossible. As an object falls deeper inside, tidal forces grow stronger. The difference in gravitational pull between the object's head and feet increases dramatically. This stretching effect, known as spaghettification, becomes extreme. Atoms are pulled apart, molecular bonds break, even atomic nuclei are stretched and torn. In small black holes, this process begins well before the event horizon is reached. An object would be destroyed long before crossing the boundary. In supermassive black holes, however, tidal forces near the horizon are much weaker. Spaghettification may occur much later, deep inside. This distinction highlights an important fact. Not all black holes behave the same way. Their size matters. The larger the black hole, the gentler the gravity at the event horizon, even though the gravity deep inside becomes unimaginably strong. As matter falls inward, space becomes increasingly distorted. Directions lose their usual meaning. What was once down becomes unavoidable. Paths that once allowed movement now all converge toward the same fate. According to general relativity, everything that crosses the event horizon eventually reaches the singularity. The singularity is not just a point in space, it is a place where the concept of space itself breaks down. Density becomes infinite. Curvature becomes infinite. Distances lose meaning. Time, as we understand it, ends. This is not poetic language. It is a literal statement about the failure of our equations. When physicists calculate what happens at the singularity using general relativity, the results become infinite. Infinite density, infinite curvature, infinite temperature. In physics, infinity is a warning sign. It tells us that a theory has been pushed beyond its domain of validity. It does not mean infinity exists physically. It means our description has failed. This failure is one of the most important clues in modern science. It tells us that general relativity, despite its success, is incomplete. At the same time, quantum mechanics, the theory that governs the smallest scales of reality, does not include gravity. Quantum mechanics describes particles, fields, and probabilities with extraordinary precision, but it breaks down when gravity becomes strong. Black holes sit precisely at the intersection of these two theories. They demand a theory of quantum gravity, a framework that can describe gravity at the smallest scales. Stephen Hawking played a central role in revealing how deep this conflict runs. Early in his career, Hawking proved that singularities are not rare oddities. Under very general conditions, gravitational collapse must produce them. If general relativity is correct, black holes must contain singularities. This result was shocking. It meant that the universe itself predicts its own breakdown points, places where our laws stop working. But Hawking did not accept that black holes were simply endpoints of destruction. He asked a radical question: what happens to information that falls into a black hole? In physics, information is not abstract. It refers to the complete description of a physical system. According to quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or transformed, but it cannot vanish completely. Black holes seem to violate this principle. If matter carrying information falls into a black hole and disappears beyond the event horizon, and if the black hole eventually evaporates, where does that information go? Is it destroyed? If so, quantum mechanics would be wrong. This puzzle became known as the black hole information paradox. For decades, physicists debated this problem. Hawking initially argued that information is lost in black holes. This view suggested that black holes introduce randomness into the universe at a fundamental level. Later, Hawking revised his position, acknowledging that information might be preserved in subtle ways. One idea is that information is encoded on the event horizon itself, spread across its surface in an incredibly compressed form. Another is that information escapes slowly through Hawking radiation, in ways we do not yet fully understand. Hawking radiation itself was a revolutionary idea. According to classical physics, nothing can escape a black hole. But when quantum effects are considered, the situation changes. Near the event horizon, quantum fluctuations constantly create pairs of particles and antiparticles. Normally, these pairs annihilate almost instantly, but near the event horizon, one particle can fall in while the other escapes. To an outside observer, it appears as if the black hole is emitting radiation. This radiation carries energy away from the black hole. Over extremely long timescales, the black hole loses mass. Eventually, it could evaporate completely. This discovery transformed black holes from eternal prisons into dynamic objects that evolve over time. But Hawking radiation raises even deeper questions. If black holes evaporate, what happens to everything that fell inside? Does the information escape? Is it destroyed? Or is it transformed beyond recognition? No definitive answer exists yet. This uncertainty highlights the limits of our knowledge. We understand black holes remarkably well from the outside. We can predict their motion. We can measure their mass and spin. We can observe their effects on nearby matter. We can even detect the gravitational waves produced when they collide. But the interior remains hidden. We cannot observe inside the event horizon. We cannot send probes. We cannot receive signals. Everything we say about the inside is inferred from theory. This does not mean the theories are meaningless. General relativity has passed every test thrown at it so far. Quantum mechanics is extraordinarily successful, but combining them remains one of the greatest challenges in science. Some theories suggest that the singularity might not exist as a true point of infinite density. Instead, quantum effects might smooth it out, replacing it with something else, a region of extreme but finite density, a bounce or even a bridge to another region of space-time. These ideas are speculative. They are not confirmed. They exist at the edge of current knowledge. Wormholes are one such idea. Solutions to Einstein's equations allow tunnels connecting distant regions of space-time. In some interpretations, black holes could be entrances to such tunnels. But whether wormholes can exist in reality, and whether they are stable, remains unknown. Other theories suggest that the interior of a black hole might encode information holographically, with all the information about the interior stored on the event horizon. This idea, known as the holographic principle, has influenced modern theoretical physics deeply. What is important is not which idea is correct, but what black holes reveal about science itself. Black holes show us that knowledge has boundaries. There are limits to observation. There are regions of reality that cannot be accessed directly. Yet even these limits are informative. By studying what we cannot see, we learn more about what we can. Black holes force us to question assumptions that once seemed absolute. That time flows the same everywhere. That information cannot be hidden permanently. That space is a fixed stage where events unfold. None of these assumptions survive close contact with a black hole, and yet black holes are not exceptions. They follow the laws of physics as faithfully as anything else. They are extreme, but they are natural. They are reminders that the universe is not obligated to match human intuition. As we step back from the edge of the event horizon, one truth becomes clear. Black holes are not just objects of destruction. They are objects of revelation. They expose the deepest tensions in our understanding of reality. In the next part, we will zoom out again. We will explore the different kinds of black holes that exist, from stellar remnants to cosmic giants. We will compare their sizes, their behaviors, and their roles in shaping galaxies. Because to truly understand black holes, we must understand not just what happens inside them, but how they fit into the universe as a whole. When people imagine black holes, they often picture a single kind of object, a dark sphere floating in space, endlessly consuming whatever comes near. In reality, black holes come in many forms, sizes, and histories. They're not a single category, but a family of objects shaped by mass, time, and cosmic environment. To understand their role in the universe, we must step back and look at the full range of black holes that exist, from those born from dying stars to giants that shape entire galaxies. The simplest way to classify black holes is by mass. Mass determines almost everything about a black hole: how large it is, how strong its gravity feels near the event horizon, how it interacts with its surroundings, and how it formed. Surprisingly, black holes with vastly different masses all obey the same basic rules. The difference lies in scale. The smallest known black holes are called stellar mass black holes. These form from the collapse of massive stars. When a star several times more massive than the Sun reaches the end of its life and explodes as a supernova, its core may collapse into a black hole. These black holes typically contain between a few times the mass of the Sun and several dozen solar masses. Despite being called small, stellar mass black holes are anything but tiny. A black hole with 10 times the mass of the Sun would have an event horizon only about 30 kilometers across. That means an object more massive than our entire star compressed into a region smaller than a city. This extreme density is what gives black holes their extraordinary gravitational influence. Stellar mass black holes are common. Our galaxy alone likely contains millions of them. Most are silent and invisible, drifting through space without interacting with much matter. They reveal themselves only when they are part of a binary system, orbiting a companion star. In such systems, gas from the companion can be pulled toward the black hole, forming an accretion disk that glows brightly. These systems were among the first strong pieces of evidence that black holes exist. One of the most famous examples is Cygnus X1, a stellar mass black hole orbiting a massive blue star. The motion of the star and the intense X-ray radiation from the surrounding disk revealed the presence of an unseen, extremely massive object. This was one of the first cases where astronomers became confident that black holes were not just theoretical ideas, but real objects in the sky. As scientists studied more systems like this, a clear picture emerged. Stellar mass black holes are the natural endpoints of massive stars. They are not exotic anomalies, they are common outcomes of stellar evolution. But stellar mass black holes are not the only kind. Between stellar mass black holes and the largest black holes in the universe lies a category that puzzled astronomers for decades: intermediate mass black holes. These black holes have masses ranging from hundreds to hundreds of thousands of times the mass of the Sun. For a long time, their existence was uncertain. They were too massive to be formed by ordinary stellar collapse, yet too small to be supermassive black holes. The question was simple but troubling. If black holes grow by merging and by consuming matter, then there should be objects that bridge the gap between small and large black holes. But for years, observational evidence was scarce. Gradually, that began to change. Astronomers found hints of intermediate mass black holes in dense star clusters. In these crowded environments, stars are packed tightly together, increasing the chances of collisions and mergers. Over time, Repeated mergers of massive stars and smaller black holes could produce a larger black hole. These environments may act as cosmic nurseries where intermediate mass black holes grow. Gravitational wave detections provided another crucial clue. When observatories detected black hole mergers involving objects heavier than typical stellar mass black holes, it suggested the presence of intermediate mass black holes. These detections confirmed that black holes exist across a wide range of masses, forming a continuous spectrum rather than isolated categories. Understanding intermediate mass black holes is important because they may be the missing link in the growth of supermassive black holes. They could be the seeds from which the giants at the centers of galaxies grew, and those giants are truly extraordinary. Supermassive black holes are the largest black holes known. They reside at the centers of galaxies and contain millions to billions of times the mass of the Sun. The supermassive black hole at the center of our Milky Way, known as Sagittarius A, has a mass of about 4 million suns. In larger galaxies, central black holes can reach billions of solar masses. What makes supermassive black holes so astonishing is not just their mass, but their size. Despite containing millions or billions of suns worth of material, their average density can be surprisingly low. A supermassive black hole with a mass of 1 billion suns could have an event horizon larger than the orbit of Mercury or Earth. Spread over that volume, its average density could be lower than that of water. This challenges intuition. It reminds us that black holes are not defined by density alone, but by the curvature of spacetime they produce. Supermassive black holes are not rare exceptions. Observations suggest that nearly every large galaxy hosts one at its center. This includes spiral galaxies like the Milky Way, elliptical galaxies, and even small dwarf galaxies. This discovery transformed astronomy. It revealed a deep connection between galaxies and black holes. Galaxies do not simply contain black holes as passive occupants. They evolve together. When supermassive black holes actively consume matter, they become some of the brightest objects in the universe. As gas falls toward the black hole, it heats up and emits enormous amounts of energy. In some cases, this energy powers jets of particles that shoot out at nearly the speed of light, extending far beyond the galaxy itself. These active galactic nuclei can outshine entire galaxies. Quasars, which are among the brightest objects ever observed, are powered by supermassive black holes feeding at extraordinary rates. These objects allow astronomers to study black holes from billions of light years away, offering a glimpse into the early universe. But supermassive black holes are not always active. Many, including Sagittarius A, are relatively quiet. They consume matter slowly, producing only faint emissions. Yet even in their quiet state, their gravity shapes the motion of stars near the galactic center. By tracking the orbits of stars near Sagittarius A, astronomers have been able to measure its mass with remarkable precision. These observations provide some of the strongest evidence for the existence of supermassive black holes. One of the most fascinating aspects of black holes is how simple they are, despite their dramatic formation histories. According to general relativity, black holes are described completely by just a few properties: mass, spin, and electric charge. This idea is often summarized by the phrase "black holes have no hair," meaning that all other details about the matter that formed them are hidden behind the event horizon. This simplicity applies to all black holes, regardless of size. A stellar mass black hole and a supermassive black hole differ mainly in scale, not in fundamental nature. Spin is especially important. Most black holes rotate, often extremely rapidly. This rotation drags space-time around with it, creating effects that influence how matter behaves near the black hole. Rotating black holes can twist accretion disks, power powerful jets, and alter the structure of the event horizon itself. The fastest spinning black holes approach a theoretical limit set by relativity. Beyond this limit, the event horizon would disappear, exposing the singularity. Whether such extreme objects can exist in reality remains an open question. Charge, on the other hand, is usually negligible. While black holes can theoretically have electric charge, in practice they quickly neutralize by attracting opposite charges from their surroundings. Another proposed category of black holes is primordial black holes. These hypothetical objects would have formed not from stars, but from density fluctuations in the early universe, shortly after the Big Bang. Depending on conditions in the early universe, primordial black holes could range from tiny objects with masses smaller than a mountain to massive black holes comparable to stars. Primordial black holes are of great interest because they could explain some forms of dark matter. However, their existence has not been confirmed. Astronomers continue to search for evidence, but for now, primordial black holes remain speculative. Regardless of their origin, all black holes share a common structure. They have an event horizon, a region of intense curvature, and an interior where known physics breaks down. What differs is how they interact with their surroundings and how they shape the universe around them. Small black holes influence their local environments. Large black holes influence entire galaxies. Supermassive black holes regulate star formation by heating and expelling gas. They can shut down the growth of galaxies or trigger bursts of star formation under the right conditions. This relationship explains why galaxies of different sizes tend to have central black holes with masses that scale with the galaxy's mass. It suggests that black holes are not merely passengers in galaxies, but active participants in their evolution. Stephen Hawking emphasized this unity among black holes. Despite their dramatic differences in size, black holes obey the same underlying laws. This universality makes them powerful tools for testing physics. By studying black holes of different masses, scientists can probe gravity across a vast range of conditions. The discovery of gravitational waves added a new dimension to this study. When black holes merge, they produce ripples in space-time that carry information about their masses and spins. These signals allow scientists to study black holes that would otherwise be invisible. Through these observations, astronomers have confirmed the existence of black holes across a wide mass range. They have observed stellar mass black holes merging, producing intermediate mass remnants. They have measured the growth of supermassive black holes over cosmic time. All of this reinforces a remarkable conclusion. Black holes are not rare, isolated phenomena. They are woven into the fabric of the universe. From the smallest stellar remnants to the largest cosmic giants, black holes represent gravity operating at its limits. They show us what happens when mass, time and space interact in extreme ways. In the next part, we will focus on one of the most mind-bending consequences of black holes. We will explore how black holes distort time itself, how different observers experience time differently, and why black holes force us to rethink what time really means. Because near a black hole, the universe does not just look strange, it runs on a different clock. Time feels simple in everyday life. It moves forward at a steady pace. Seconds turn into minutes, minutes into hours, and hours into years. No matter where you are or what you're doing, time seems to flow the same way for everyone. This assumption feels so natural that we rarely question it. Yet it is wrong. Time is not universal, not fixed, and not independent of the universe around it. Black holes reveal this truth more clearly than anything else we know. Long before black holes were accepted as real objects, scientists believed that time flowed identically everywhere. Isaac Newton imagined time as a constant river, flowing evenly throughout the universe, unaffected by matter or motion. This view worked well for centuries, explaining the motion of planets and the behavior of objects on Earth. But as observations became more precise, cracks began to appear in this picture. Albert Einstein changed everything. In his theory of relativity, Einstein showed that time is not separate from space. Instead, space and time are woven together into a single structure called spacetime. Motion and gravity affect how time flows. The faster you move, the slower your clock ticks relative to someone at rest. The stronger the gravity you experience, the slower your time passes compared to someone farther away. These effects are small in everyday life, but they are real. Satellites orbiting Earth experience weaker gravity than people on the surface, and their clocks tick slightly faster. If this difference were not corrected, GPS systems would drift and become useless within hours. Time is already behaving differently around us, even on Earth. Near a black hole, these effects become extreme. A black hole represents the strongest gravitational environment in the universe. It is a place where space-time is curved so severely that the flow of time itself is distorted beyond ordinary comprehension. To understand this, imagine two observers. One remains far away from the black hole. The other moves closer and closer to it. For the distant observer, time flows normally. Their clock ticks steadily. They watch as the other observer approaches the black hole. But as the falling observer gets closer, something strange happens. Their movements appear to slow down. Their signals take longer to arrive. Their clock seems to tick more slowly. This is not an illusion. It is the result of gravitational time dilation. As gravity becomes stronger, time slows down relative to regions of weaker gravity. Near a black hole, this effect becomes so extreme that from the distant observer's point of view, the falling observer never actually crosses the event horizon. Instead, they appear to freeze just above it, fading away as their light is stretched to longer and longer wavelengths. This stretching of light is known as gravitational redshift. Light climbing out of a strong gravitational field loses energy, shifting toward redder wavelengths. Near the event horizon, this redshift becomes infinite. The light becomes so stretched that it can no longer be detected. The falling observer effectively disappears. From the distant observer's perspective, time near the black hole grinds to a halt. But this is only half the story. From the falling observer's own perspective, time flows normally. Their heart beats at the same pace. Their thoughts occur as usual. They do not feel time slowing down. When they reach the event horizon, nothing special happens locally. There is no sudden change, no barrier, no flash of light. They cross it without noticing. This difference in perspective is not a contradiction. It is a fundamental feature of relativity. Time does not have a single, universal flow. It depends on where you are and how you're moving. Black holes expose this truth in the most dramatic way possible. The event horizon marks a point where the structure of space-time itself changes. Outside the horizon, it is possible to move away from the black hole if you have enough energy. Inside the horizon, this is no longer true. The direction outward becomes as inaccessible as the past. To understand why, it helps to think about time as a direction rather than a substance. In everyday life, you move forward in time whether you want to or not. You cannot stop it, you cannot reverse it. Inside a black hole, the direction toward the center plays a similar role. It is not just a place you can go, it is the future. Once inside the event horizon, moving toward the singularity is as inevitable as the passage of time itself. Avoiding it would require moving backward in time, which is forbidden by the laws of physics. This idea challenges everything we think we know about cause and effect. In ordinary circumstances, causes precede effects. Events unfold in a predictable sequence. Near a black hole, this sequence becomes distorted. Different observers disagree on the order of events. What one observer sees as happening slowly, another experiences as normal. There is no single timeline that applies to everyone. This raises a natural question. Could black holes allow time travel? The short answer is no, at least not in any practical or currently understood way. While black holes do create extreme distortions of time, they do not allow travel into the past. They can allow one observer to experience less time than another, effectively jumping into the future of the outside universe. But returning to the past remains forbidden. For example, an astronaut who approached a black hole and then escaped might find that much more time had passed for people far away than for themselves. In this sense, black holes could act as one-way time machines to the future, but escaping after crossing the event horizon is impossible, and surviving close encounters would be extraordinarily difficult. This limitation highlights an important distinction. Time dilation is not time travel in the science fiction sense. It does not allow changes to history or communication with the past. It simply reflects the flexibility of time itself. Stephen Hawking was deeply interested in these questions. He explored the relationship between gravity, time, and the structure of the universe. One of his most famous ideas was the chronology protection conjecture, which suggests that the laws of physics prevent the formation of closed time-like curves, paths that would allow travel into the past. Black holes play a key role in this discussion. Some solutions to Einstein's equations suggest that rotating black holes could, under extreme conditions, create regions where time loops back on itself. But whether such regions can exist in reality, or whether they are destroyed by instabilities, remains an open question. What is clear is that black holes force us to rethink what time actually is. In classical physics, time is a background parameter, something that exists independently of events. In relativity, time becomes dynamic. It is shaped by matter and energy. Near a black hole, time stretches, slows, and twists in ways that defy intuition. This has profound implications for the nature of reality. Consider the idea of simultaneity. In everyday life, we assume that events happening at the same time are the same for everyone. Relativity shows this is not true. Near a black hole, different observers cannot even agree on whether an event has already happened or is still occurring. This breakdown of shared time makes it impossible to construct a single, objective history of events near a black hole. Instead, reality depends on perspective. Inside the event horizon, this dependence becomes absolute. According to general relativity, once inside, all paths lead to the singularity in a finite amount of proper time. No matter how large the black hole, the journey from the horizon to the singularity takes a limited amount of time for the falling observer. For a stellar mass black hole, this time could be fractions of a second. For a supermassive black hole, it could be hours. During this time, the structure of space-time becomes increasingly distorted. Tidal forces grow, directions lose meaning. The distinction between space and time collapses completely. At the singularity, time ends. This statement is not metaphorical. In the equations of general relativity, the singularity is not a point in time that comes after other events. It is a boundary beyond which time cannot be extended. The future simply stops. This idea is deeply unsettling. It suggests that the universe contains places where time itself is destroyed. But once again, infinity signals a breakdown of theory. It is likely that a complete theory of quantum gravity would modify this picture, replacing the singularity with something else. What that something is remains unknown. Hawking. Radiation adds another layer to the story of time. According to Hawking's calculations, black holes are not eternal. Over incredibly long timescales, they lose mass by emitting radiation. This means that black holes have lifetimes. They are born, they evolve, and they eventually die. For stellar mass black holes, this process would take far longer than the current age of the universe. For supermassive black holes, it would take unimaginably longer. But the principle is profound. Even black holes are subject to time. This raises a new question. If black holes evaporate, what happens to time inside them? What happens to the future that seemed inevitable once the event horizon was crossed? These questions lie at the heart of the information paradox. They force physicists to confront the relationship between time, entropy, and information. Entropy is often described as the arrow of time. It measures disorder and gives time its direction. Black holes are deeply connected to entropy. Hawking showed that black holes have entropy proportional to the area of their event horizons. This was a revolutionary insight. It linked gravity, thermodynamics, and quantum mechanics in a single framework. The fact that black holes have entropy means they have microscopic degrees of freedom. Something is happening at a deeper level than classical physics can describe. Time, in this view, may emerge from more fundamental processes. It may not be a basic ingredient of the universe, but a consequence of how information is organized and evolves. Black holes push this idea to its limits. They compress enormous amounts of information into tiny regions of space-time. They hide information behind horizons. They radiate energy and entropy back into the universe. They blur the line between past and future. By studying black holes, physicists hope to uncover the true nature of time itself. This is why black holes are sometimes called the ultimate time machines, not because they allow easy travel through time, but because they reveal how flexible, fragile, and deeply connected time is to the structure of the universe. They show us that time can slow, stretch, and even end. They show us that the flow of time depends on gravity and motion. And they show us that our everyday experience of time is only a small part of a much richer cosmic reality. In the next part, we will address some of the most persistent fears and misconceptions about black holes. Do they destroy everything? Could one ever threaten Earth? Are they as dangerous as movies suggest? To answer these questions, we must separate dramatic fiction from scientific reality. Because while black holes are among the most extreme objects in the universe, they are far less chaotic than most people imagine. Few objects in the universe are as misunderstood as black holes. Popular culture has turned them into cosmic villains, endless vacuums roaming space and devouring everything in their path. Movies show stars being ripped apart. From across the galaxy, planets spiraling helplessly inward, and entire universes collapsing into darkness. These images are powerful, dramatic, and almost entirely wrong. The truth is more subtle, more interesting, and far less terrifying. Black holes are not cosmic vacuum cleaners. They do not hunt matter. They do not pull objects in from great distances any more aggressively than other massive objects do. In fact, from far away, a black hole behaves just like any other object with the same mass. Gravity does not suddenly become dangerous just because something is a black hole. This idea alone overturns one of the most common fears. A black hole does not destroy everything around it simply by existing. Distance matters, mass matters, motion matters. To understand why, imagine a simple scenario. Take our sun and magically compress it into a black hole without changing its mass. This is impossible in reality, but it is a useful thought experiment. If this happened, Earth would not suddenly be pulled inward. Our planet would continue orbiting exactly as it does now. The gravitational pull at Earth's distance would remain the same. Nothing catastrophic would happen. This surprises many people because we instinctively associate black holes with extreme danger. But gravity depends on mass, not on whether an object is a star or a black hole. The sun's mass determines Earth's orbit, not the sun's size or appearance. The danger of a black hole begins only when you get very close. Black holes have a region called the event horizon, beyond which escape is impossible. But this region is extremely small compared to cosmic distances. For a stellar mass black hole, the event horizon may be only a few tens of kilometers across. For a supermassive black hole, it may be larger than the orbit of Earth, but still tiny compared to a galaxy. Unless something comes close to that region, it remains safe. So why do black holes have such a destructive reputation? The answer lies in what happens to matter that does fall too close. When gas, dust, or stars approach a black hole, they do not simply vanish quietly. They are torn apart heated to extreme temperatures, and accelerated to near-light speeds. This process releases enormous amounts of energy. Ironically, the most violent and destructive effects associated with black holes occur outside them, not inside. As matter falls toward a black hole, it forms an accretion disk. Friction and magnetic forces within the disk heat the material until it glows intensely, emitting radiation across the electromagnetic spectrum. This radiation can be far more powerful than the light from the stars in an entire galaxy. In some cases, black holes launch jets of particles that shoot out from their poles at nearly the speed of light. These jets can extend thousands or even millions of light years into space, affecting vast regions of the surrounding universe. These phenomena can look terrifying. They can destroy nearby stars, strip galaxies of gas and reshape cosmic environments, but they are not random acts of destruction. They follow precise physical laws. Most importantly, they require matter to already be close to the black hole. A black hole sitting alone in empty space is harmless. This brings us to another common fear. Could a black hole ever threaten Earth? The short answer is no. There are no known black holes close enough to pose any danger to our planet. The nearest known black holes are thousands of light years away. Even if a stellar mass black hole passed through our solar system, which is extraordinarily unlikely, its effects would depend on how close it came. If it passed at a distance comparable to that of the Sun, Earth's orbit would change, but not catastrophically. If it passed very close, it could disrupt planetary orbits. But the odds of such an encounter are vanishingly small. Space is vast. Stars and black holes are tiny compared to the distances between them. Another fear often raised is the possibility of black holes being created on Earth, particularly in particle accelerators. This idea gained attention when large experiments were planned to collide particles at high energies. Some worried that these collisions could create tiny black holes that might grow and consume the planet. This fear is unfounded. If microscopic black holes could be created in such experiments, they would evaporate almost instantly through Hawking radiation. They would pose no danger. Moreover, nature itself performs particle collisions at energies far higher than any human-made machine, such as when cosmic rays strike Earth's atmosphere. If dangerous black holes could form this way, Earth would not still exist. The universe has already tested these scenarios for billions of years. Another widespread misconception is that black holes constantly grow by consuming everything around them. In reality, most black holes grow very slowly. Matter must lose energy and angular momentum to fall in. This is not easy. Most material that approaches a black hole ends up orbiting it or being ejected rather than falling straight in. Accretion is often inefficient. Supermassive black holes grow over billions of years, primarily during periods when galaxies collide or experience bursts of star formation. Even then, growth is regulated. As black holes become active and emit energy, they can heat or expel nearby gas, shutting down their own food supply. This self-regulating behavior explains why black holes do not grow without limit. It also explains why black holes are not destroying the universe. Another fear is the idea that black holes could eventually swallow everything. This notion misunderstands how gravity works on cosmic scales. Black holes do not expand endlessly. Their event horizons grow only when they gain mass. They do not spread outward like a wave. Even in the far future, black holes will not consume the entire universe. In fact, the expansion of the universe is accelerating. Distant galaxies are moving away from each other faster and faster. This expansion limits the reach of gravity on the larger scales. Black holes are powerful, but they are not omnipotent. The universe is not collapsing into a single black hole. What about stars being destroyed by black holes? This does happen, but it is rare and localized. Occasionally, a star passes too close to a black hole and is torn apart by tidal forces. These events, known as tidal disruption events, produce dramatic bursts of radiation that astronomers can observe. But these events occur on timescales of thousands or millions of years and affect only a tiny region of space. They do not trigger chain reactions or widespread destruction. Even at the centers of galaxies where supermassive black holes reside, most stars orbit safely for billions of years. The Milky Way's central black hole, Sagittarius A, has existed for billions of years. During that time, it has not consumed the galaxy. It has not pulled stars inward en masse. The vast majority of stars in our galaxy will never come close to it. This calm reality contrasts sharply with fictional portrayals. Why then do black holes inspire so much fear? Part of the reason is psychological. Black holes represent loss of control. They symbolize places where escape is impossible, where known rules break down, and where information disappears. These ideas trigger deep unease. Another reason is that black holes challenge intuition. They do not behave the way everyday objects do. When intuition fails, fear often fills the gap. Science replaces fear with understanding. When we understand that black holes obey precise laws, that they interact with their surroundings in predictable ways, and that they are constrained by distance and energy, much of the fear dissolves. Black holes are not agents of chaos. They are expressions of order at its extreme. They also play a constructive role in the universe. By regulating star formation, supermassive black holes help determine the structure of galaxies. By driving energetic jets, they redistribute matter and energy across vast distances. By merging and emitting gravitational waves, they allow us to study the universe in entirely new ways. Black holes are not destroyers of everything. They are sculptors. Even their most extreme effects are limited to their immediate surroundings. Beyond that, their influence fades with distance, just like any other gravitational object. One of the most fascinating realizations is that black holes can be among the most stable objects in the universe. Once formed, they can persist for timescales far longer than stars, planets, or even galaxies. In this sense, black holes are not symbols of sudden destruction, but of long-term cosmic evolution. Stephen Hawking emphasized this perspective. While he explored the deep mysteries of black holes, he also worked to correct public misconceptions. He repeatedly explained that black holes are not threats lurking in space, but natural outcomes of gravity and stellar evolution. Understanding this distinction is crucial. Fear distracts from wonder. Black holes are not frightening because they destroy indiscriminately. They are fascinating because they reveal how the universe works under extreme conditions. When we remove the myths, what remains is something far more impressive. A universe governed by consistent laws, capable of producing objects that stretch those laws to their limits, yet still remain orderly. In the next part, we will explore how scientists study something that cannot be seen directly. We will look at the clever methods used to detect black holes, measure their properties, and even image their shadows. Because one of the most remarkable achievements of modern science is not just discovering black holes, but learning how to study the invisible. A black hole emits no light. It reflects nothing. It produces no visible surface. By every ordinary definition of observation, it should be impossible to detect. And yet, humans have not only discovered black holes, but measured their masses, tracked their spins, watched them collide, and even captured images of their shadows. This achievement is one of the most remarkable successes in the history of science, because it required learning how to study something that cannot be seen directly. The story of detecting black holes is not a story of a single breakthrough. It is a story of patience, indirect evidence, clever reasoning, and the willingness to trust mathematics and observation over intuition. Scientists did not find black holes by pointing telescopes at empty darkness. They found them by watching how black holes affect everything around them. The simplest way to detect a black hole is to look for its gravitational influence. Gravity does not hide. Even if an object emits no light, its mass still shapes the motion of nearby stars and gas. By carefully tracking these motions, scientists can infer the presence of something massive and invisible. This approach was used long before black holes were accepted as real. Astronomers had already learned to discover unseen objects by their gravitational effects. Neptune, for example, was discovered because Uranus's orbit behaved strangely. Something unseen was tugging on it. The same logic applies to black holes, but on a far more extreme scale. In some star systems, astronomers observe a visible star orbiting an invisible companion. By measuring the speed and shape of the star's orbit, they can calculate the mass of the unseen object. If that mass is too large to be a white dwarf or neutron star, the only remaining explanation is a black hole. This method led to the first strong black hole candidates. One of the most famous is Cygnus X1. Astronomers observed a massive blue star orbiting something invisible, while intense X-ray radiation poured from the system. The invisible object was too massive to be anything other than a black hole. This discovery marked a turning point. Black holes were no longer just mathematical predictions. They were real astrophysical objects. X-rays play a crucial role in black hole detection. When matter falls toward a black hole, it rarely falls straight in. Instead, it spirals inward, forming an accretion disk. Friction, magnetic fields, and collisions within the disk heat the material to millions of degrees. At these temperatures, the disk emits X-rays. X-ray telescopes in space revealed countless bright sources scattered across the sky. Many of these sources were traced back to binary systems containing black holes. These observations allowed scientists to study black holes indirectly by analyzing the radiation emitted by their surroundings. But stellar mass black holes are only part of the story. The most astonishing discoveries came from studying the centers of galaxies. For decades, astronomers suspected that something massive lurked at the heart of the Milky Way. Stars near the galactic center moved at incredible speeds, far faster than could be explained by visible matter alone. The orbits of these stars traced tight paths around an invisible point. By tracking these orbits over many years, astronomers calculated the mass of the unseen object. The result was stunning. Millions of times the mass of the Sun was packed into a region smaller than our solar system. No known object other than a black hole could explain this. This invisible object became known as Sagittarius AI. The evidence was overwhelming. Similar observations in other galaxies revealed the same pattern. Wherever astronomers looked closely enough, they found supermassive black holes at galactic centers. These discoveries reshaped our understanding of galaxies themselves. Yet even with this evidence, black holes remained invisible. Scientists knew they were there, but they had never seen anything resembling one. That changed in 2019. In that year, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow. This achievement was not the result of a single telescope, but of a global network of radio observatories working together as one Earth-sized instrument. The challenge was enormous. The black hole being imaged lay in a galaxy millions of light years away. Its apparent size on the sky was smaller than an orange on the surface of the moon. To resolve such a tiny feature, astronomers needed a telescope with unprecedented resolution. By synchronizing observatories across the planet and using precise atomic clocks, scientists effectively created a telescope as large as Earth itself. They observed radio waves emitted by hot gas swirling near the event horizon. By combining data from multiple locations, they reconstructed an image. What emerged was not a photograph in the traditional sense, but a carefully assembled representation of the black hole's shadow. A dark central region surrounded by a glowing ring of light, warped by extreme gravity. This image matched predictions made by general relativity with remarkable accuracy. For the first time, humanity had visual confirmation of an event horizon. This image was more than a technical achievement. It was a profound validation of decades of theory. Einstein's equations, written more than a century earlier, had predicted exactly this kind of structure. But black holes reveal themselves in other ways too. In 2015, scientists detected gravitational waves for the first time. These ripples in space-time were produced by two black holes spiraling toward each other and merging. The signal lasted only a fraction of a second, but it carried information about the masses and spins of the black holes involved. Gravitational wave observatories such as LIGO and Virgo opened an entirely new window on the universe. Unlike light, gravitational waves pass through matter almost unaffected. They allow scientists to observe events that would otherwise be hidden. Since that first detection, dozens of black hole mergers have been observed. Each one confirms the existence of black holes and provides new insights into their properties. These observations have revealed black holes heavier than previously expected, spinning in unexpected ways and forming binary systems that challenge existing models. Gravitational waves allow scientists to study black holes that emit no light at all. They reveal black holes in complete darkness. This ability represents a revolution in astronomy. Another powerful tool for studying black holes is variability. Accretion disks around black holes often fluctuate in brightness. These fluctuations occur on timescales that depend on the size of the black hole. By studying these patterns, scientists can estimate black hole masses and probe conditions near the event horizon. Jets provide another clue. Some black holes launch narrow beams of particles at nearly the speed of light. These jets emit radiation across the spectrum and can extend far beyond the host galaxy. By studying jets, scientists learn about magnetic fields, rotation, and energy extraction from black holes. Stephen Hawking emphasized the importance of combining theory with observation. He understood that black holes could not be studied by direct exploration, but by careful inference. His theoretical work on black hole radiation provided predictions that guide observational searches, even though Hawking radiation itself is far too weak to detect from astrophysical black holes. Yet the indirect evidence is powerful. Black holes influence their environments in ways that are impossible to ignore. They shape galaxies, regulate star formation, and drive some of the most energetic phenomena in the universe. By studying these effects, scientists can learn about black holes even without seeing them directly. The detection of black holes also relies on exclusion. Scientists consider all possible explanations for observed phenomena and eliminate those that do not fit. When an object is too massive, too compact, and too dark to be anything else, the conclusion becomes unavoidable. This method requires caution and skepticism. Astronomers do not label something a black hole lightly. Each claim must be supported by multiple lines of evidence. Over time, the consistency of these observations has built overwhelming confidence. Today, black holes are no longer rare or exotic. They are common, measurable, and central to our understanding of the universe. What makes this achievement even more impressive is that it was accomplished without leaving Earth. No probe has ever visited a black hole. No spacecraft has crossed an event horizon. Everything we know comes from light, motion, and waves detected across vast distances. This is a triumph of human reasoning. By trusting mathematics, developing sensitive instruments, and interpreting subtle signals, scientists have uncovered objects that seem designed to remain hidden. Black holes teach us that observation does not always require sight. Sometimes, understanding comes from watching shadows, listening to vibrations in space-time, and tracing invisible influences. In the next part, we will look far into the future. We will explore how black holes evolve over cosmic time, how they may eventually evaporate, and what role they play in the ultimate fate of the universe. Because black holes are not just relics of the past, they are key players in the universe's future. When we look at black holes, it is easy to think of them as local objects, extreme but isolated. A collapsed star here, a supermassive giant there. But black holes are far more than cosmic curiosities. Over billions of years, they have helped shape galaxies, regulate the growth of stars, and influence the large-scale structure of the universe itself. And far into the future, long after stars burn out and galaxies fade, black holes may become the final dominant objects left behind. To understand the fate of the universe, we must understand the role black holes play across cosmic time. In the early universe, shortly after the Big Bang, matter was spread almost evenly. Tiny differences in density slowly grew under the influence of gravity. Regions with slightly more matter pulled in even more, forming the first stars and galaxies. At the centers of these growing galaxies, black holes began to appear. How the first supermassive black holes formed remains one of the biggest open questions in astrophysics. Some may have grown from the remnants of the first massive stars. Others may have formed through the direct collapse of enormous clouds of gas. Whatever their origin, once these black holes existed, they began to shape their surroundings in profound ways. As gas fell toward these early black holes, it heated up and released vast amounts of energy. This energy did not simply vanish. It pushed back on the surrounding gas, slowing or even halting star formation in some regions. In other cases, shock waves and a turbulence triggered new bursts of star formation. In this way, black holes became regulators of galactic growth. Galaxies and black holes grew together. Observations show a strong relationship between the mass of a galaxy's central black hole and the mass of the galaxy itself. This connection suggests that black holes are not passive passengers in galaxies. They are active participants in their evolution. Over billions of years, galaxies merged. When galaxies collided, their central black holes eventually spiraled toward each other and merged as well. These mergers released enormous amounts of energy in the form of gravitational waves, reshaping space-time itself. With each merger, black holes grew larger and their influence extended farther. Today, we live in a universe filled with black holes of all sizes. Stellar mass black holes drift quietly through galaxies. Supermassive black holes sit at galactic centers, sometimes active, sometimes dormant. Together, they form a hidden population that outweighs the visible stars in some regions. But this is only the present chapter of the story. To understand the ultimate fate of the universe, we must look far beyond the present into timescales so vast that human language struggles to describe them. Stars do not live forever. Even the longest-lived stars will eventually exhaust their fuel. Over trillions of years, star formation will slow and then stop as galaxies run out of gas. The universe will enter an era of darkness, populated by stellar remnants, white dwarfs, neutron stars, and black holes. In this future universe, black holes will be among the most massive and persistent objects left. For a long time, scientists believed that black holes were eternal. Once formed, they would last forever, silently consuming anything that wandered too close. This view changed dramatically in the 1970s when Stephen Hawking made one of the most surprising discoveries in modern physics. Hawking showed that black holes are not completely black. According to quantum mechanics, empty space is not truly empty. It is filled with fluctuations, where pairs of particles and antiparticles briefly appear and then annihilate each other. Near the event horizon of a black hole, these fluctuations can be separated. One particle falls into the black hole, while the other escapes. To an outside observer, it appears that the black hole is emitting radiation. This radiation, now known as Hawking radiation, carries energy away from the black hole. Because energy and mass are equivalent, the black hole slowly loses mass over time. Given enough time, it will shrink and eventually disappear entirely. This idea was shocking. It meant that black holes are not eternal prisons. They are temporary objects with lifetimes, just like stars. The timescales involved are enormous. A stellar mass black hole would take far longer than the current age of the universe to evaporate. A supermassive black hole would take vastly longer, far exceeding trillions upon trillions of years. But the principle is clear. Given enough time, black holes fade away. This realization has profound implications for the fate of the universe. As stars die out and galaxies grow dark, black holes will become the dominant sources of structure. They will slowly merge, grow, and then, over incomprehensible timescales, begin to evaporate. During this era, the universe will be cold and sparse. Matter will be rare. Most particles will be isolated. Black holes will stand as islands of mass in an expanding sea of emptiness. Eventually, even these islands will disappear. As black holes lose mass through Hawking radiation, their temperature increases. This may seem counterintuitive, but smaller black holes radiate more strongly than larger ones. As a black hole shrinks, it emits radiation faster and faster. Near the end of its life, the process accelerates dramatically. The final moments of a black hole's evaporation would release a burst of energy. What exactly happens at this final stage is still uncertain. Quantum gravity effects likely become important. But once the black hole is gone, nothing remains of it except radiation. This leads to one of the deepest questions in physics. What happens to the information that fell into the black hole? If black holes evaporate completely, and if information is destroyed, then the laws of quantum mechanics are violated. If information is preserved, it must escape somehow, encoded in Hawking radiation or stored in subtle correlations. This question, known as the black hole information paradox, remains unresolved. It sits at the heart of modern theoretical physics and continues to drive research into quantum gravity, string theory, and holography. The fate of information is closely tied to the fate of time itself. As the universe expands, it cools. Entropy increases. The arrow of time points forward toward greater disorder. Black holes, with their enormous entropy, play a key role in this process. Hawking showed that black holes have entropy proportional to the area of their event horizons. This means that black holes are among the most entropic objects in the universe. They represent extreme states of disorder, where information is compressed and hidden. As black holes evaporate, entropy is released back into the universe in the form of radiation. This radiation is extremely diffuse, spread across vast distances. Over time, the universe approaches a state of maximum entropy, where no useful energy remains. This scenario is often called the heat death of the universe. In this final state, there are no stars, no galaxies, no black holes, only a thin soup of particles and radiation drifting through an ever-expanding space. Time continues to pass, but nothing meaningful happens. Black holes, once symbols of destruction, become key players in this quiet ending. They gather matter, lock it away for eons, and then slowly release it back into the universe. They delay the march toward equilibrium, acting as reservoirs of structure in an otherwise dissolving cosmos. Some theories suggest alternative endings. If the expansion of the universe slows or reverses, a big crunch could occur, collapsing everything back together. In such a scenario, black holes would merge into ever larger structures, possibly forming a single, final black hole. However, current observations suggest that the expansion of the universe is accelerating, making this outcome unlikely. Other ideas propose that black holes could spawn new universes. In some speculative models, the interior of a black hole might connect to a new expanding region of space-time. In this view, black holes could be cosmic seeds, giving birth to new universes as ours fades. These ideas are highly speculative and not supported by direct evidence, but they highlight how black holes force us to think beyond familiar boundaries. Even the question of whether black holes truly evaporate completely remains open. Hawking radiation has not been observed directly because it is far too weak to detect from astrophysical black holes. Yet the theoretical framework supporting it is strong. If Hawking radiation is real, then nothing in the universe is permanent. Not stars, not galaxies, not even black holes. This impermanence reshapes how we think about cosmic time. The universe is not a static stage, it is a process. Structures form, evolve, and dissolve. Black holes are among the longest-lasting structures, but they too are temporary. Stephen Hawking often emphasized this perspective. He saw black holes not as ends, but as transitions. They reveal how the universe transforms matter, energy, and information across unimaginable timescales. They also remind us of our place in cosmic history. We live in a brief era when stars shine brightly, galaxies are rich with structure, and black holes are actively shaping their surroundings. This era will not last forever, but it is long enough for conscious beings to arise, ask questions, and uncover the laws that govern reality. In that sense, black holes are not symbols of despair, they are symbols of continuity. They connect the birth of stars to the far future of the universe. They link gravity, time, and information in ways that challenge and inspire us. In the next part, we will turn to the questions that remain unanswered. What truly lies inside a black hole? Is information destroyed or preserved? Are black holes connected to other universes? And why do these questions matter for the future of physics? Because even after decades of study, black holes still hold secrets that may redefine our understanding of reality itself. After more than a century of study, black holes remain among the most mysterious objects in the universe. We can measure their mass, observe their influence, detect their mergers, and even image their shadows. Yet at their core, black holes confront us with questions that science has not yet answered. These questions are not minor details. They strike at the foundations of physics itself. They challenge our understanding of space, time, information, and reality. The first and most fundamental question is simple to state and extraordinarily difficult to answer. What is inside a black hole? According to general relativity, everything that crosses the event horizon is drawn inevitably toward the singularity. At this point, density becomes infinite, space-time curvature becomes infinite, and the laws of physics as we know them break down completely. But infinity in physics is not a solution. It is a signal that a theory has failed. Most physicists do not believe that singularities exist as literal points of infinite density in nature. Instead, singularities are seen as placeholders, markers showing where our equations stop working. They indicate that a deeper theory is needed, one that can describe gravity at the quantum level. This leads directly to the greatest missing piece in modern physics, a theory of quantum gravity. General relativity describes gravity on large scales with extraordinary accuracy. Quantum mechanics describes the behavior of particles on the smallest scales with equal success. But these two theories are fundamentally incompatible. Black holes are the places where both must apply at once. Inside a black hole, gravity is extremely strong, and quantum effects cannot be ignored. Yet we do not have a complete framework that combines these effects into a single, consistent description. Various approaches attempt to solve this problem. String theory suggests that fundamental particles are not points, but tiny vibrating strings, and that gravity emerges naturally from their behavior. Loop quantum gravity proposes that space-time itself is quantized, composed of tiny discrete units, rather than a smooth continuum. Other approaches explore entirely different mathematical structures. All of these theories remain unconfirmed. They offer possible ways to replace the singularity with something finite, perhaps a region of extreme but limited density, or a bounce that avoids infinite collapse. But without experimental evidence, these ideas remain speculative. Another profound question concerns information. In classical physics, information can be lost. If you burn a book, the information encoded in its pages appears to be destroyed. But in quantum mechanics, information is fundamentally conserved. It can be scrambled or hidden, but it cannot disappear completely. Black holes seem to violate this principle. When matter falls into a black hole, it crosses the event horizon and becomes inaccessible to the outside universe. If the black hole eventually evaporates through Hawking radiation, and if that radiation is purely random, then the information about what fell in is lost forever. This scenario contradicts quantum mechanics. This conflict is known as the black hole information paradox, and it has been one of the most intense debates in theoretical physics for decades. Stephen Hawking initially argued that information is lost in black holes. This view implied that the universe is fundamentally unpredictable at a deep level. Over time, however, Hawking revised his position, acknowledging that information might be preserved in ways we do not yet fully understand. One possibility is that information is encoded on the event horizon itself. This idea suggests that the surface area of the black hole contains all the information about its interior, compressed into a two-dimensional boundary. This concept is known as the holographic principle. According to the holographic principle, the universe may be describable as information stored on lower dimensional surfaces. Black holes provide the clearest hint that this idea might be correct. If true, this would mean that reality itself is fundamentally different from how we perceive it. The three-dimensional world we experience could be an emergent projection of deeper information encoded on boundaries. Another possibility is that information slowly escapes through Hawking radiation, encoded in subtle correlations between particles. In this view, Hawking radiation is not completely random. It carries faint imprints of the information that fell into the black hole. This idea preserves quantum mechanics but requires a radical rethinking of how black holes work. It suggests that the event horizon is not a simple, passive boundary, but an active region with complex quantum structure. Yet another proposal involves the idea of firewalls. Some physicists have suggested that the event horizon might not be smooth at all, but instead a violent region that destroys infalling matter and releases information. This idea challenges the equivalence principle, a cornerstone of general relativity, which states that free-falling observers should experience smooth physics. Firewalls remain highly controversial. They illustrate how black holes force physicists to choose between deeply held principles. Do we preserve general relativity at the cost of quantum mechanics? Or preserve quantum mechanics at the cost of relativity? Or is there a deeper framework that resolves the conflict? No one knows yet. Another question that captures the imagination is whether black holes are connected to other universes. Solutions to Einstein's equations allow for structures known as wormholes, tunnels connecting distant regions of space-time. In some interpretations, black holes could be entrances to such tunnels. Matter falling into a black hole might emerge elsewhere, perhaps in another region of our universe, or in an entirely different universe. These ideas are mathematically allowed, but their physical reality is uncertain. Most wormhole solutions are unstable. They collapse before anything can pass through them. Maintaining a traversable wormhole would require exotic forms of matter with negative energy density, which may not exist in nature. Nevertheless, the idea persists because it touches on fundamental questions about space-time topology and causality. If wormholes exist, they could revolutionize our understanding of space, time, and connectivity in the universe. Closely related is the question of whether black holes give birth to new universes. Some speculative models suggest that the interior of a black hole might undergo a bounce rather than collapsing into a singularity. This bounce could initiate a new expanding region of space-time, effectively creating a new universe. In this view, black holes are not endpoints, but beginnings. Our own universe could be the interior of a black hole formed in a parent universe. This idea is deeply speculative and currently untestable. But it illustrates how black holes stretch scientific imagination while remaining grounded in mathematical possibility. Another unresolved issue concerns the nature of the event horizon itself. Is the event horizon a sharp boundary, or is it fuzzy at the quantum level? Does it store information? Does it radiate energy in subtle ways beyond Hawking radiation? Does it change dynamically as matter falls in? Some theories suggest that the event horizon may not be a single, well-defined surface, but a fluctuating region influenced by quantum effects. If so, the classical picture of a smooth boundary may be an approximation. This has implications for how black holes interact with their surroundings and how information is processed. Time is another unresolved puzzle. Inside a black hole, time appears to end at the singularity. But if singularities are replaced by something else, in a quantum theory of gravity, what happens to time? Does it continue? Does it loop? Does it lose meaning entirely? Time is already a mysterious concept in physics. In quantum mechanics, time plays a different role than in relativity. Black holes amplify this tension. Understanding time inside black holes may be key to understanding time itself. Another open question involves the ultimate fate of black holes. Hawking radiation suggests that black holes eventually evaporate completely. But what happens in the final moments? Does the black hole disappear smoothly? Does it leave behind a remnant? Does it explode? Does it transition into something else? Some theories propose that black holes leave behind stable remnants, tiny objects containing all the information that fell in. Others suggest that the final evaporation releases information in a final burst. Without a complete theory of quantum gravity, these questions remain unanswered. Even observationally, black holes still surprise us. Gravitational wave detections have revealed black holes heavier than expected, spinning in unexpected directions, and merging in environments that challenge existing models. Each new observation forces scientists to revise their understanding. Black holes also raise philosophical questions. If there are regions of the universe that are fundamentally unobservable, what does that mean for science? Can we claim to understand reality if parts of it are forever hidden? Black holes challenge the idea that the universe is fully knowable. They introduce horizons not just in space but in knowledge. Yet history suggests that horizons move. What was once thought unknowable often becomes understood with new ideas and tools. Black holes themselves were once dismissed as impossible. Today they are central to astrophysics. The unanswered questions surrounding black holes are not signs of failure. They are signs of progress. They mark the boundary between what we know and what we are about to discover. Stephen Hawking often emphasized this point. He believed that black holes, rather than being obstacles to understanding, are gateways to deeper knowledge. They force us to confront the limits of our theories and inspire the search for more complete descriptions of nature. In this sense, black holes are not just objects of study. They are guides. They point toward a future where gravity and quantum mechanics are unified, where information is fully understood, and where the structure of space-time is revealed at its most fundamental level. In the final part, we will step back from equations and theories and ask a more human question. Why do black holes matter to us? Why are we so fascinated by them? And what do they teach us about curiosity, humility, and our place in the universe? Because in the end, black holes are not just about the universe out there. They are about how we seek to understand it. Black holes are often described as distant, abstract objects, far removed from everyday life. They exist thousands or millions of light years away, hidden in the depths of space, unreachable by any spacecraft. At first glance, it may seem reasonable to ask why they matter to us at all. Why should humans care about objects we will never visit and forces we will never experience directly? The answer is deeper than astronomy. Black holes matter because they change how we understand reality itself. Throughout history, human progress has often come from confronting ideas that challenge intuition. The Earth is not the center of the universe. Time is not absolute. Matter and energy are interchangeable. Each of these realizations reshaped not only science, but how humanity sees its place in the cosmos. Black holes belong in this tradition. They force us to abandon comfortable assumptions and replace them with a more honest picture of the universe. One reason black holes matter is that they reveal the limits of our knowledge. In a world where technology advances rapidly and information feels limitless, black holes remind us that nature still holds mysteries beyond our reach. There are places where observation stops, where equations break down, and where certainty gives way to questions. This is not a weakness of science, it is its strength. Science does not promise complete answers. It promises a method, a way to test ideas, discard what fails, and refine what survives. Black holes sit at the edge of this process. They are where our best theories meet their boundaries. They show us not just what we know, but what we do not yet understand. Black holes also matter because they unify different areas of science. Gravity, quantum mechanics, thermodynamics, information theory, and cosmology all intersect at black holes. Few objects demand such a broad range of ideas. By studying black holes, physicists are forced to think across disciplines, searching for connections that might otherwise remain hidden. This unifying role is not accidental. Black holes are extreme expressions of nature's rules. When those rules are pushed to their limits, their deeper structure becomes visible. Black holes act like stress tests for the universe, revealing which ideas hold up and which need revision. Stephen Hawking understood this better than most. Despite severe physical limitations, he devoted his life to understanding black holes not because they were frightening, but because they were illuminating. His work showed that black holes are not just sinks of matter, but thermodynamic objects with temperature, entropy, and evolution. This insight linked gravity to quantum theory in a way that no other object could. Hawking often emphasized that black holes are not about destruction, but about transformation. Matter falls in, energy comes out, information is scrambled but not necessarily lost. Time flows in unfamiliar ways, but it still follows rules. Black holes turn simple questions into profound ones. They ask us to reconsider what it means to know something. In everyday life, knowledge feels concrete. You see an object, measure it, and understand it. Black holes challenge this model. You cannot see them directly. You infer their existence from shadows, motions, and subtle signals. You build confidence not through direct contact, but through consistency across many observations. This process mirrors how humans often understand complex systems, from climate to economics to biology. Black holes remind us that indirect evidence can be powerful, and that understanding does not always require direct access. Black holes also matter because they shape the universe we inhabit. The galaxies that host stars, planets, and life have been influenced by black holes since their formation. Supermassive black holes helped regulate star formation, shaped galactic structure, and influenced how matter organized itself on the largest scales. Without black holes, the universe would look very different. The Milky Way might not exist in its current form. The conditions that allowed Earth to form might never have arisen. In this sense, black holes are part of our cosmic ancestry. They are not separate from us. They are part of the chain of events that led to our existence. At a deeper level, black holes matter because they challenge human intuition about time. Near a black hole, time slows, stretches, and even appears to end. Different observers experience different versions of in reality. There is no single universal clock ticking the same way everywhere. This realization has implications beyond physics. It challenges the way we think about cause and effect, memory, and the passage of moments. It reminds us that our experience of time is local and limited, shaped by conditions rather than absolute truths. Black holes also force us to confront impermanence. Even the most massive objects in the universe are temporary. Stars die, galaxies merge, black holes evaporate. Over vast timescales, nothing remains unchanged. This perspective can feel unsettling, but it can also be grounding. It places human existence within a larger narrative, one that emphasizes process over permanence. Meaning does not come from lasting forever, but from participating in a universe that evolves. In this way, black holes connect science to philosophy. They raise questions about determinism and unpredictability, about whether information is truly preserved, about whether reality is fundamentally smooth or discrete, about whether space and time are basic ingredients or emergent properties. These questions are not abstract curiosities. They influence how we build theories, design experiments, and interpret observations. They shape the future of physics. Black holes also matter because they inspire imagination without abandoning discipline. They invite speculation but demand rigor. They encourage creativity but punish carelessness. This balance is essential to scientific progress. It is easy to turn black holes into metaphors for fear, emptiness, or destruction. But science replaces metaphor with mechanism. It shows that black holes are not malevolent forces, but natural outcomes of gravity operating under extreme conditions. Understanding this difference matters. Fear thrives on misunderstanding. Curiosity thrives on clarity. When people learn that black holes do not roam the universe, consuming everything, that they obey predictable laws, and that they play constructive roles in cosmic evolution, fear gives way to wonder. This shift is important not just for astronomy, but for how society relates to science more broadly. Complex ideas can be intimidating. Black holes demonstrate that even the most extreme phenomena can be understood through patience, evidence, and reason. They also demonstrate the power of collaboration. No single person discovered black holes. No single telescope revealed them. Their study required generations of scientists, engineers, mathematicians, and observers working together across cultures and continents. The first image of a black hole was not a triumph of one mind, but of collective effort. It symbolized what humanity can achieve when curiosity is shared and knowledge is built collaboratively. This lesson extends beyond science. Black holes matter because they show us what it means to explore responsibly. They remind us that some questions take time, that some answers require humility, that progress often comes slowly, through incremental advances rather than sudden revelations. They also remind us that uncertainty is not failure, it is an invitation. Every unanswered question about black holes points toward future discoveries, new theories, new instruments, new ways of thinking. The unknown is not a void, it is a frontier. As technology advances, we will learn more. We will detect more gravitational waves. We will image more event horizons. We may find evidence for quantum gravity effects. We may resolve the information paradox. Or we may uncover new mysteries that force us to rethink everything again. This openness is the heart of science. Black holes matter because they teach us how to live with questions. They teach us that understanding is not about final answers, but about deeper questions. That knowledge is provisional. That curiosity is a strength, not a weakness. They also remind us of scale. Human concerns often feel urgent and absolute. Black holes place those concerns within a cosmic context. They do not diminish human experience, but they reframe it. They show that our ability to ask questions about the universe is itself extraordinary. In a universe that contains objects capable of bending space, stopping time, and hiding information behind horizons, the fact that conscious beings can understand even part of this story is remarkable. Black holes are not just objects in space. They are mirrors. They reflect our desire to know, our willingness to confront uncertainty, and our capacity for wonder. They stand as reminders that the universe is not obligated to make sense to us, yet it often does if we are willing to listen carefully. In the end, black holes matter not because they threaten us, but because they challenge us. They ask us to expand our imagination, sharpen our reasoning, and accept that reality is richer than intuition suggests. They show us that the universe is not simple, but it is intelligible. Not complete, but coherent. Not fully known, but deeply knowable. And as long as questions remain, the journey continues. Before you close this video, pause for a moment and think about what you've just explored. Black holes are not just objects drifting silently through space. They are places where the universe reveals its deepest rules, where gravity bends time, where information is questioned, and where our understanding reaches its edge. We often imagine discovery as something loud or dramatic, but the most important discoveries are quiet. They change how we think rather than what we see. Black holes do exactly that. They remind us that reality is far stranger than intuition and far richer than imagination alone. What makes this even more remarkable is that everything you've learned comes from careful observation, patience, and human curiosity. No one has ever visited a black hole. No probe has crossed an event horizon. Yet by watching shadows, listening to ripples in space-time, and trusting evidence over instinct, we've uncovered truths hidden billions of light years away. And the story is far from over. Some of the biggest questions remain unanswered. What truly happens inside a black hole? Is information lost or preserved? What does gravity look like at the smallest scales? The next discoveries may completely rewrite what we think we know about space, time, and reality itself. If this journey made you look at the universe differently, stay curious. Science moves forward because people keep asking better questions, not because everything is already known. If you want to continue exploring ideas like this, you know what to do. Stay with the channel, share the curiosity, and keep questioning the universe. Because the darkest places in space often shine the brightest light on understanding. Thank you for watching.